How could I write that in with congruent statements if the diagonals bisect each other? Like, where would I put my congruence ticks? Here, the dashes. Somebody can come up and do it if they want.
Between A and D.
Okay, between A and
B, D.
okay,
B, E.
BE, there we go. Okay, BE and ED. Okay, those guys, right? They have to be congruent because that diagonal has been cut in half, been bisected by the other one. But it's reciprocal. This guy also is getting cut in half, so don't I have to do that? Right? Make sense? Okay, so we gotta see if that's the case. So we gotta measure those, I guess, don't we? Right? Let's measure those little pieces of the diagonals and see. So let's measure AE. Measure distance. Okay, what color are these going to be? Yeah. Oh, I don't think yellow's going to show up. Ooh, that's bad.
That's black.
Black. We haven't done black, have we? It'll be black. Okay. Okay, so then we got to do, that was what? AE. Let's do CE. What's it going to be? Same thing. How about that? BE. Okay, and DE. Now those two are going to be different but congruent to each other, right? Make sense? Isn't that what we just said?
Yeah.
Okay, good. All right, now notice if I tweak this thing then, I want you to watch all those measurements. Parallelograms, there's some symmetry going on there. There's some relationships. If I tweak this, I've built this so it's going to stay a parallelogram. Cool. All right, those relationships are maintained. Anything I do up here to this is going to keep it a parallelogram, right? Okay, now let's investigate what happens if we do some special things to this parallelogram. What's going to happen if I, let me make this just a little bit. So just a little bit this way. Okay. So now what's going to happen if I scoop point A over so that this point angle DAB, right, or a second, what do we call it? DAB is right, oh, BAD, right there. Okay, this guy right here, I'm going to make that a right angle. Oops, maybe I'm not.
Segment B.
Okay, I think I have to pick a different one, because the way I've got these things anchored. Oh, never mind, there we go, now I can. Okay, I want to make angle DAB a right angle, so tell me when we get to BAD. Let's get close.
Stop
right
it.
there. Oh, what'd they all do? What'd they all do?
Well, they all went to 90 degrees.
They all became 90 degrees. They all became right angles. So when one goes, in a parallelogram, if one goes to 90, they all go to 90. And what do we call that shape? No, that's you've known that one since about kindergarten. What's that called? That's a rectangle, sure. Okay. So the definition of a rectangle really is a special parallelogram. Yes, Dan?
What would happen if you moved the midpoint? His question.
Okay, I'll do that in a second. That's a good question. We'll tweak it and see. I don't know if I can. Maybe I can. We'll see. So a rectangle is a special kind of parallelogram that just happens to have 4 right angles, right? So it gets all the parallelogram properties for free because everything I draw up there is a parallelogram, right? When I made this into a rectangle, I still kept all that parallelogram stuff also. But do you notice anything else that happened when I did that? Was there something else up here that happened? Is it more symmetric than it was before?
Are you referring to the side lights or this?
Well, I'm referring to, yeah, some of the measurements up there. Some of the measurements that used to be different are now the same.
Well, all the inner like line measurements, like CE and AE, are all the same.
Yeah, look at that. Okay, look what happened to the diagonals, right? The diagonals, it used to be like this, right? Those two were congruent and those two were congruent, but they were all different. Now they're still bisecting each other, but they're all the same. So what's that telling us? Isn't that telling us that that this whole diagonal must be congruent to that whole diagonal if all the pieces are congruent. Does that make sense? Okay, so the additional thing we get all that stuff that goes with the parallelogram, but if it's also a rectangle, we also know we get the extra property that the diagonals are congruent. Okay? So that's the additional piece that we get. Does that make sense?
Yeah.
Okay, now someone wanted to do an experiment here. Wanted to see what happened if we, and I'm kind of curious too, what if I move E? Oh, it just moves the whole thing. Yeah, okay. Okay, now let's try something else. Let's go back to where we were before. So we've just got we got a parallelogram, but this time I'm going to drag one side of this parallelogram over so that all four of the sides are congruent. Okay.
Question before you go.
Yeah, go ahead.
Can you bring one side down so it's kind of like almost make it like a triangle kind of thing? Or does it move the whole thing?
No, it moves the whole thing. If I move it, it's always going to stay a parallelogram. So I can't, the way I've built this thing, I can't do anything but a parallelogram.
Okay.
It's going to always keep that same, the same properties. So let's grab this side right here. I'm going to drag that over if possible. And this, I don't know if I can do this or not. Let's see. Where are my sides? Right there. So I've got to do two things at once, which I'm a hard time with. My wife will vouch for that too. There we go, okay? How about that? So what do we notice here? Anything new? See, all I've done here, I've just kept, those are all congruent now. Okay, so all these are congruent. Do we notice any new properties? And I'll make this a little quicker. The answer is no, you don't. You don't notice any yet. But there are some things going on there. We have to look at the diagonals. There's two things going on with the diagonals. Does anybody want me to check something up here with the diagonals? Make some measurements.
Well,
What do you think? Any suggestions?
I have questions.
I'm just curious about some angles up here. What do you think?
Why is it that if they were all at one point the same, then why is AE and CE longer than BE and DE?
Okay, because this is no longer a rectangle.
Oh.
Right? I tweaked it so it's no longer a rectangle, but now all the sides are congruent. What is this called, by the way? What if all the sides are congruent?
Equilateral?
No, well, it's
Square.
equilateral.
Square.
An equilateral quadrilateral
Rhombus.
is a rhombus. Yeah, this is a rhombus.
What's a rhombus?
No, it's a triangle.
That's a rhombus. A rhombus is just a quadrilateral parallelogram that's got four congruent sides, is by definition a rhombus. Now let's measure a couple things here. Let's measure, just to speed this up, I'm just going to tell you what I'm going to measure. Let's measure these interior angles right here. Let's measure this guy, and this guy, and this guy, and this guy. Actually, maybe we don't even have to measure them all, but we could. So I'm going to measure angle BEC. Anybody want to suggest what it might be? Oh, it's supposed. It's not. Okay, this thing is just slightly tweaked, is what's going on.
I was close.
Okay, let me just. I'm gonna try to get this thing so it's back on track. Oh, why is it not gonna do that? That's crazy.
I think that's close enough to 90.
It is pretty close.
Now you're just getting fine.
It's just bugging me that it's not right though. What if, can I go out to like 9? There we go. I bet this will work. Now watch if I go.
There you go. That's good. Go shot.
Oh, I see what I'm doing. This darn thing.
It'd seem easier if you just type in an angle measure and turn it. Can you do that?
I think I can set it up that way, but I don't have it done. Did that do it? Oh my gosh, I didn't do it. Well, you get the idea, right? You get the idea?
Yep.
Okay,
It's close enough.
what if I actually had one of these built? Wouldn't that be handy?
But one of
What if I actually had from last period even, how about? Wouldn't that be slick if I did? Go ahead. Yeah. Okay, so what about this? Let's try this one now. So if I scoot this guy over. Oops, what am I doing? Sorry it's taking so long, but I about got it here. Be patient with me. There we go. Oh, it's still off by the tiniest bit. Anyway, so long story short, what is this trying to do?
Trying to equalize this.
What are those interior angles trying to be?
Equal
Look at all these guys right here.
90.
They're trying to be 90, aren't they?
But
Right? Does that make sense? Okay. So, you know what I wonder if I can do? Oh, this would be slick. Hang on. I think I know how I can do this. Can I construct a right angle, you think, out of those? Oh, I guess not. Oh, that's too bad. I thought I could. I thought it was gonna be really slick there. Oh well. Anyway, so one thing. Here's another thing we get. Back on track. Sorry that took so long. I got you off track. We got to reel back in. Focus back in. So if this is a rhombus, if all the sides are congruent in this parallelogram, one other thing that's true that comes with being a rhombus is that the diagonals are perpendicular. They'll always be perpendicular. They meet at right angles. Okay? What else? Well, I've already done some other measurements here too. I did this last period. But look down here. If I measure these angles, measure of angle ABE, I'll make this green. So here's ABE. That's this guy right here, right? And the measure of angle DBE right there, those are congruent. In fact, would you believe me if I told you that if I were to look at how the diagonals cut the opposite angles, that those would also be congruent, and those would be congruent, and those would be congruent? Because they would, if I measured them all. Okay? So all that stuff is true. The other property then of a rhombus is it's a parallelogram with all the, the stuff that comes with being a parallelogram. Also, I get perpendicular diagonals, and how do I say that? The diagonals do what to the opposite angles? Bisect them, exactly. They cut them in half. Two congruent parts, right? So those two things come also. Those are for free. Now, what is going to happen here? Last issue. No, I'll give you a try. Come on in. Come on in. You can try it. Give it a try. Okay, so now what happens here if I do both of those at the same time? So I'm going to keep the sides. I'm going to keep the sides congruent, but I'm going to make the angles 90 degrees. Look how symmetrical this is if I do that. So oh, did I get it? I got it. Look at that. Now look at all that stuff. Yeah. No applause. Money, please. So if I do all that stuff, look, everything is now, I have total symmetry with this thing. All the sides are congruent, all the angles are congruent. Notice that the diagonals are still bisecting, or they're bisecting each other. They're still meeting at perpendicular segments, right? They're meeting at right angles. So what do we call this from kindergarten? Square? Square. So a square has all the properties of both. It's both a rhombus and a rectangle, right? Okay. So enough of that probably. Let's summarize this stuff. And this will be it for today.
What?
No, sorry. Sorry. Okay, so here's our summary real quick.
I come up for those with Keith's side.
Yes, ma'am. You go ahead, take it fast. Okay, so we know special parallelograms, right? We got normal parallelograms, and then we've got some special parallelograms. A rhombus is a parallelogram with 4 congruent sides. Rectangle's a parallelogram with 4 right angles, and a square gets both all at once. All that stuff is true. It's equilateral, and it has 4 right angles. Here's one of the things I want you to look at. This is kind of like that. This will be a logical challenge for you. Kind of makes sense of this.
Especially
This is called a Venn diagram. It's really important that you understand how to use a Venn diagram. They don't just apply to math. Venn diagrams could apply to
building a house.
English, building a house. They could apply to anything. Like, for example, if you were talking about parts of speech, you could have a parts of speech Venn diagram with the verbs and the nouns and things that cross over. It's all, you can look at political affiliations of people, and you can do all kinds of things. All a Venn diagram does is it takes a bunch of relationships and it writes them as sets and subsets. So think what this is saying here. We've got this box of all possible parallelograms. Every possible parallelogram that you could make, all infinity of them, are dumped into this box that holds them all. Within that box, there are some subsets. So I'm going to have a balloon within the box that's filled up with all possible rhombuses. I'm going to have another balloon that's filled up with all possible rectangles, another subset. Now, what does it mean that the square is a part of both of those balloons?
Well,
What does that tell you about a square?
they can be classified as both.
Yeah, that it is both at the same time. So you could say that the set of squares, right? Look at this little set of squares here in the middle that's kind of that slightly different shade of green. AJ, it's that slightly different shade of green. That set of squares is the intersection of the set of rhombuses and the set of rectangles, isn't it? It's where they overlap, right? Okay, so let's look at some, I want you to answer some questions for me here. Don't say it out loud yet. I want you to think about this. I'm going to give you 3 or 4 questions, and the answer to each question is going to be always, sometimes, or never. True. So here's the statement. A rhombus is a rectangle. Always, sometimes, or never true. You see these things on lots of big time tests. You'll see it on my test, but you'll see it on some bigger tests. SAT tests, Oaks tests, things like that too. So you gotta kind of wrap your brain around this a little bit. Now, one strategy is you could just try all 3 statements and see which one makes sense. Does anybody want to suggest an answer to this one? Sometimes? Agree with that? Sounds good to me. Now, that's correct. Now, let's see why it is. Now, here's another way to look at these. If a statement is always true, I can only find true examples, right? I can't find counterexamples. I can't find false examples. If a statement is never true, I can find no true examples. I can only find false examples, right? But if a statement is sometimes true, I ought to be able to find at least one of each. Does that make sense? So if I can find one example and one counterexample, that guarantees the answer is sometimes. So let's use green checks for true examples, red X's for counterexamples, and see if you can identify on our picture up there, on our diagram. I don't want to put you out there again. Just see if we can make it for the rest of the period. Focus. Put that away.
Hey, she messed it up.
I don't care. Put it away. So somebody give me an example of a rhombus that is a rectangle. Where would that be on the graph? I can put a green check there. A rhombus that is a rectangle. Square. Right there. Okay, agreed? Because that is a rhombus that fits in this set that's also a rectangle. So if we can come up with one red X, can we find an example of a rhombus that is not a rectangle? That guy, for example, right? Everybody agree? Because I can find at least one of each, the answer has to be sometimes. Okay? How about the next one? A parallelogram is a rectangle. Can you find a true example of a parallelogram that is a rectangle? Well, I could pick a square if I wanted to. Sure, I could even just pick that one if I wanted, right? That's a rectangle, but it's also a parallelogram, right? Can you find a counterexample? Can you find a parallelogram that is not a rectangle? Yeah, that guy or that guy right there, right? I got at least one of each, and so it's sometimes. right? Okay, I'm gonna give you another one.
Well, can you use a reference on map?
What?
Can you use a reference on application?
Sure.
Yes.
So how about this? A rectangle is a parallelogram. Sometimes, always, or never true. What do you think?
Never.
You don't know what you're talking
I don't.
There are lots of alwayses. Yeah.
Always is this.
Always is. Okay, because I can find every example that I pick in here, if it's a rectangle, it's obviously a parallelogram, right? But can I find an example of a rectangle that's outside of this box of parallelograms?
about.
No. I can't,
Oh.
right? Probably a more mathematical way of saying that would be to say that because the set of rectangles is a subset of the set of parallelograms, all rectangles have to be contained in the bigger set of rectangles, or parallelograms, right? We wouldn't have to be that fancy about it, we can just kind of see it this way, right? Okay, so,
Question.
yes,
It's kind of a dumb question, but why do they call that a diamond shape? I've never seen a diamond shape like that.
well, that's, okay, that's really, probably when you say diamond,
Okay.
diamond isn't really a mathematical word so much. When we say diamond, we kind of know what we mean. Is that a diamond? Yeah, it is, but could this also be a diamond? It's a good question. I mean, it kind of depends how you think of a diamond, right? If you agree, if this is your definition of a diamond, then a diamond is sometimes a rhombus, but not always. If that's your definition of a diamond, then it is a rhombus. Okay?
Okay.
But that's not really a word. Instead, we're going to use the word rhombus or the word kite. We'll get to kite later. That's a kite right there.
That makes
If
more
those
sense
two
than
sides are congruent and those two sides are congruent, it's called a kite.
Cool.
All right, so moving on. Okay, so let's summarize.
Yeah.
Okay, this is kind of an important thing here. I want to show you something. Properties of special parallelograms. We know that if it's a rectangle, we get all the stuff that comes with being a parallelogram, but we get some extra. Okay, we get some extra stuff too. The extra stuff, if I scoot ahead here a little bit, the extra stuff is that for a rhombus, it went out of order. For a rhombus, we know that the diagonals are perpendicular, right? There's the extra thing we get. And we know that the diagonals bisect opposite angles. For a rectangle, we also know that the diagonals are congruent. Okay, but there's something else here. Last thing I want to draw to your attention, because this is kind of important, and I don't want to minimize it because it's at the very end. If we say something like this, okay, I want to show you something. Look at this part of the statement. It says a parallelogram is a rectangle if and only if its diagonals are congruent. Okay. Whenever you see that terminology in math, and you see it a lot, if and only if. That's what we call in math a biconditional statement. Here's how I always want you to think about that. A biconditional statement is equivalent to a bidirectional arrow. So what that really means is, I can say this two ways, and they're both included. I can say if rectangle, then diagonals are congruent. That's always true. But I could also turn it around and say, if the diagonals are congruent, then rectangle.
Don't do it.
So it goes both ways. Okay, whenever you see an if and only if, it's like saying I can do both of those conditional statements. I can do if this, then that, or flip it around. It'll work both ways. Okay. So what that tells us, though, that it does that, there's a little artifact of that that's important. Okay. Here's what we find. Okay, I get these little corollaries. I don't care if you know that they're called corollaries. Think of them as shortcuts. for a rhombus, I don't have to show, for something to be a rhombus, I don't have to show that it's a parallelogram first, and then that it's a rhombus, even though a rhombus is a special kind of parallelogram. Okay, here's what I can do. I can just say, because a rhombus is a unique kind of shape that's got this if and only if relationship. AJ, grab your stuff. This isn't working. Grab your stuff and go out here. No, just grab your stuff and go out in the hall for the last couple minutes. Don't leave till the bell rings.
Fair enough.
Okay. So here's our corollary. A quadrilateral is a rhombus if and only if it has 4 congruent sides. I don't have to show anything else. All I have to show is that if a quadrilateral has 4 congruent sides, it's a rhombus. Guaranteed. That's the definition of a rhombus. Sure, it's also a parallelogram, and I get all the other stuff that comes with it, but it's very easy to prove that it's a rhombus. All I got to show is that the 4 sides are congruent. That's it. All 4 sides are congruent. I get everything else with it. If I can show, for example, that a quadrilateral has 4 right angles, that makes it a rectangle. I don't have to go through the hassle of showing that it's a parallelogram first. I get all the parallelogram stuff for free. But if it's a quadrilateral, and it's got 4 right angles, that's a rectangle, guaranteed. Okay, that's all I need. And then if I can show both of those things, it's a square. I don't know, that's all I have to say. If it's equilateral and it has right angles, it's a square. I get all the other stuff for free. Okay, does that make sense? It'll make more sense when we actually look at a proof.